Hi, my name is Ghosh, and today I'll be presenting Learning to Reach Goals via Iterated Supervised Learning. This is joint work with collaborators at UC Berkeley and at CMU. Now, a lot of our successes in machine learning have centered around this workhorse of supervised learning. And it's a simple formula. We know that with enough data and the right inductive biases, supervised learning with a neural network works really well. So if we can reduce our problem into a prediction problem, whether classification or regression, then we can start to leverage the success we've had with neural networks. But this story doesn't quite work so well when the problem that we care about isn't of prediction. And this is roughly the situation that we find ourselves in reinforcement learning, where we want to learn useful policies, but we want to do it through a feedback loop, where the agent continually interacts in an environment, collecting trajectories and using these trajectories to update the agent. And just to touch on how RL algorithms differ from supervised learning problems, value-based methods, which bootstrap their value estimate, their objective is of regression, but it's a highly non-stationary regression problem that has theoretical and practical difficulties with neural networks. The other class, policy gradient methods, don't correspond to a prediction problem at all, instead taking a gradient update of a very particular form that forces them only to use data collected from the most recent policy, which is highly limiting. And now, while we certainly can and we have combined these methods with neural networks, there's a lot of room for improvement. And one way to potentially realize this improvement is to have an RL algorithm that's able to better leverage this workhorse of supervised learning. How can we actually go about doing that, though, making the RL problem look more like supervised learning? Well, suppose for a second that instead of needing to learn through feedback, we instead had access to a human expert. This corresponds to the imitation learning setting, where there's a very simple way of taking policy learning and turning it into a supervised learning problem. If the expert provides us a data set of optimal demonstrations that tells us what the best action to take at any state is, then we can run an algorithm called behavioral cloning, which trains our neural network policy on this data set using supervised learning, predicting the optimal action A given the state S. And this is a very practical algorithm, and it's been used to learn complex behaviors from image-based and other high-dimensional observations in the real world. And ultimately, what makes behavioral cloning tick is that when we have access to a data set of optimal trajectories, then imitating these trajectories using supervised learning leads to good policies. Okay, well, let's try to take this idea and bring it back into the RL formulation, where instead of human experts, we have to learn from feedback. One naive attempt to try this might be to just change our policy update in the RL loop and just have it imitate the trajectory we just collected. But this is clearly not going to work. In behavioral cloning, the trajectory we were imitating was known to be optimal. But in RL, this trajectory is being collected by our own suboptimal policy. But I want to make this work. And maybe one way to do this might be to, before we imitate the trajectory, let's try to modify the trajectory in a way that makes it an optimal demonstration, at which point imitating it would make sense. And supposing for a second that we had access to such a device that made trajectories optimal, then this loop would lead to an RL algorithm that uses supervised learning to learn its policy. But coming back to reality, in the general RL setting, there's no way to implement this mechanism that makes trajectories optimal without having additional external information, like a human expert. Now, obviously, this wouldn't be an interesting talk if this is where it ended. What we're going to show is that for the class of goal-reaching problems, this mechanism can actually be efficiently implemented. And this leads to an incredibly simple algorithm for the goal-reaching problem that follows this exact cycle, collecting trajectories from the policy, modifying them to become demonstrations of optimal behavior, and then imitating this modified experience, continually looping the process. Let's quickly review some basics. In the goal-reaching setting, the agent is asked to not perform one specific task, but rather one of many possible tasks. At the beginning of each episode, a new task is chosen for the agent randomly. Each task corresponds to reaching a particular goal state in the environment. And the agent is provided with an indicator reward as to whether or not this desired goal was actually reached. Now, this problem encapsulates a number of useful applications, especially in robotics. Say, for example, a robot that navigates a maze might want to reach all possible goal locations in the maze. A household robot that needs to do chores can have chores specified as goals. If the robot must set a dinner table, then the goal can be an image of a prearranged dinner table. If the robot needs to clean the room, then the goal can be set to a picture of a clean and tidy room. So this goal-reaching problem is actually a pretty broad and important problem. In this setting, how are we actually going to go about making a trajectory optimal? Well, as an example, suppose we have this robot that's asked to place the blue block on top of the green block. And this robot hasn't really learned a good policy yet. So whatever trajectory the agent collects isn't going to do that. Let's say it instead shuffles around and puts the blue block on top of the red block. Now, this trajectory doesn't tell us much about how we can actually go about placing the blue block on the green block, but it's a great demonstration of how we can place the blue block on the red block. And as a general maxim, any trajectory, even if it's uninformative for reaching the desired goal, is a demonstration for reaching the goal that was actually achieved. And now we can see how we can start taking suboptimal trajectories and turning them into optimal ones by relabeling the desired goal for the trajectory post hoc to be the goal that was actually achieved. In this case, just changing the desired goal to have the blue block on top of the red block turns this trajectory into a demonstration of optimal behavior. Let's think about this a little more carefully. Is this trajectory we collected necessarily a demonstration for how to get to the goal as soon as possible? No, not necessarily. Maybe the agent took a long and windy path to get to the desired goal. But what we do know is that the agent did achieve the goal at the final time step h. So whatever action the agent took is an optimal action for getting to the goal within some period of time, at time step t within h minus t time steps. And of course, we can make this more general. The agent not only achieved the final state in the trajectory, it also achieved all of the intermediary states as well. So we can actually relabel the desired goal to any of these intermediary states that was achieved as well, and create a new optimal demonstration for reaching that goal. And this mechanism of changing the desired goal to be the goal that was actually achieved leads to our algorithm, which we call goal conditioned supervised learning, GCSL for short. GCSL follows this exact flow that we described. It iteratively collects trajectories, replaces the desired goal to turn it into an optimal demonstration, and then imitates this newly created demonstration using supervised learning, and repeats this process over and over again. Let's walk through one round of GCSL with our robot. As we said, this robot collected a trajectory, wanting to place the blue block on the green block, but ends up placing it on the red block instead. In the policy update step, GCSL takes this trajectory and modifies the desired goal state to be the final goal that was actually achieved. Then we take this newly created demonstration and perform goal-conditioned behavioral cloning on it, which is this supervised learning problem where the neural network policy has to predict the optimal action when passed in the current state, the desired goal state, and the horizon, which is the time frame in which the agent needs to learn to achieve the goal. Now, there's one question here. Why do we need this to be a loop? After all, how can we actually improve on imitating optimal demonstrations? It turns out to be crucially important in this process that this is iterated. Let's see why. At the beginning of training, the policy that's being used to collect data only sees a small subset of states. And so when it performs relabeling and imitation, it will only learn how to reach these goals that are nearby. It's only having done so will the agent actually encounter new goals that are further away or more difficult to achieve. So by repeating this relabeling and imitation step, the policy will get better at reaching a wider and wider range of goals, and as a consequence, start to witness even more goals and new ways to reach them. If this agent never iteratively collected data, then it would only ever learn a policy to reach the most easy to achieve goals. Now, there are a couple of interesting aspects about this algorithm that I'd like to comment on. The first is that since this idea of goal relabeling works with any trajectory, this algorithm is actually completely off policy. It can relabel and imitate any trajectory, whether it's trajectories collected from a previous iteration, from an offline dataset, or even an expert demonstrator. In practice, this means we can maintain a replay buffer of trajectories, and at policy update time, sample a random trajectory and perform the GCSL update with it. The second point to note is that this final policy update that we have is a simple supervised learning problem. When the action space is discrete, it corresponds to a classification problem, and when the action space is continuous, it's a regression problem. And unlike in the value estimation problem in RL, the targets for this regression problem are stationary. Finally, let's talk about how this relabeling step in GCSL relates to goal relabeling in value-based methods. For example, hindsight experience replay. Because although the two are similar, there are some key conceptual differences. Now, hindsight experience replay relabels transitions. Given a transition, it constructs a new fictitious transition, pretending that the desired goal was something else, G'. And this idea allows a value-based method to use this transition to help estimate the value for any other arbitrary goal, G' in the environment. GCSL, on the other hand, only relabels the goal to be one of the achieved goal states later in the trajectory. And it does so with the realization that only for this specific choice of imagined goal, we have something stronger. We no longer have to use this fictitious transition to estimate a value function. We can actually use it instead as a demonstration of optimal behavior. And this allows us to move away from this unstable learning primitive of temporal difference learning, and instead switch it with a more robust and stable one, imitation learning. And this is a big conceptual gap, because even if we try to mimic GCSL's choice of goals with hindsight experience replay, we won't recover anything like this algorithm, because under the hood, hindsight experience replay still needs to use this imagined data to learn a value function, whereas GCSL uses it to directly learn a policy with supervised learning. Now, we analyze GCSL formally, borrowing tools from the analysis of behavioral cloning and policy gradient methods. If you're interested in the details, please do check out the paper, but at a high level, we drew two conclusions. First, when data collection and optimization are iterated, GCSL actually optimizes a lower bound on the true RL objective. And here, this repeated self-imitation is important to get the result. And second, under certain conditions on the environment, we actually have a performance guarantee that when we can sufficiently minimize the supervised learning objective, then we are guaranteed to have learned a near optimal policy. Now, in our empirical evaluation, we tried to understand how GCSL compares to more classical value-based and policy gradient approaches. And one thing that we were especially keen on understanding is whether or not, because this algorithm relies on supervised learning, if it actually retains the benefits that we get with supervised learning on neural networks. So the first thing we evaluated is the performance and compared it to a policy gradient method, PPO, and a value-based method, TD3 with hindsight experience replay, on a set of 5 benchmark goal-reaching tasks. This figure here shows the average distance to the goal for the learned policy through the training process. And what you see is that GCSL, which is in blue in this figure, not only learns faster, but also asymptotically achieves lower distance to the goal on most tasks. Now, the second question we were interested in understanding is whether GCSL can better leverage demonstration data compared to other RL methods. And to put this in context, currently the best way to train a value-based methods with demonstrations is quite complicated, requiring collecting more data to stabilize learning and running auxiliary objectives. In contrast, to use demonstrations with GCSL, we can just treat them like any other trajectory that we might have collected and run the GCSL objective of relabeling and imitation. And when we empirically compared these two methods, we found that GCSL is able to learn far more gracefully in the presence of demonstrations compared to TD3. Finally, we investigated the sensitivity of this algorithm to hyperparameters, the hope being that since supervised learning is relatively robust to these things, this would carry over to GCSL. And this is actually what we found in practice. We evaluated GCSL and TD3 across a number of different hyperparameter choices, varying the network architecture and the frequency of gradient steps. In this figure, we plotted the distribution of performance across these many hyperparameter choices. With GCSL in blue, the distribution of performance is relatively concentrated around its mean, which means it isn't very sensitive to these choices, but TD3, on the other hand, is. To summarize, in this talk, we presented GCSL, an algorithm for learning to reach goals that uses supervised learning to learn a policy. Since GCSL uses supervised learning to learn this policy, the algorithm is very simple, easy to implement, and robust to the choice of hyperparameters. If you're interested in learning more, please check out our paper, our code base, or join us at the poster session. Thank you.